Oh no.
Good morning.
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 How are you?
Okay. Need it louder. Loud.
Can you hear me well?
No, not really.
What's the problem? So
You're clipping quite a lot. I think the gain is too high.
I'll try to reduce it a bit, but
Doing opening the window or more light.
any better now?
Slightly, yeah.
Yeah. Because if we start on Zoom with too much background noise and you cannot hear me, it's gonna be a bad start. So normally it readjusts after 5 minutes. It readjusts a little better. By the way, I started recording this meeting straight away. I don't know if I'm going to do the same in all the others. Please let me know if there are any possible problems. Okay.
Here's the boys.
What you guys have been told by Simon about the organization of the Zoom classes? Are there any particular guidelines? Because we don't know too much. We've been told to do more or less the way we want, but of course we would like to be as consistent as possible. I don't know if it's going to happen, but we'll see. Did you have any particular guidelines for that?
I think it's just up to the lecturer's personal preference.
Because my idea, then I'll show you when I start when everybody is in more or less. I will start with a very brief introduction of this course, this organic course for the third year, and then we'll go through the proper lecture. My point is, I will try. Okay, they told us not to be much longer than 1.5 hours. We'll see today if it's going to be 1.5 hours only. I cannot promise today, and anything like for all the rest, anything is work in progress with this weird stuff. So I would like to have any feedback from you, and we will readjust everything in due course if we find better ways or we find that something is not working at all. So please let me know if it's too slow, it's too fast, it's too messed up, because we will readjust accordingly. Of course, I need to cover all the material, all the possible material. So technically speaking, it's not going to be, my plan is not going to be much different from the other years. So the only thing is that we're moving to Zoom. I will try to split sometimes in breakout rooms. We will see later, and we'll see if it works. I know Joel yesterday tried with the first year, and probably Simon did the same. I don't know how well did it go, but I think after the first week we will all I don't know, reconvene and see how it's going. So any feedback from you guys, either in chat, by email, anything, please let me know. So to start with, shall we have a break today between the two parts? I think for today we might have to do it because it might be longer than other days, but we'll find out. Normally speaking, I always ask you if you prefer to go for the full material or if you prefer having a break in between. So let me know what you prefer. To me, it's good both ways. Since we're not going to have a whiteboard, apart from the one that we can use with Zoom, I wanted to ask anyone, do you have any of the Wacom pen? I think Simon might have suggested that. Or if we use the whiteboard, I am pretty sure, or on my slides, I'm pretty sure you can use the mouse. It's not going to be very comfortable, but it's something. So if someone has any of these kind of pens or tablets that you can use, it's probably going to be easier and faster. I'm going to use one. And let's see how it goes. I didn't hear anything from any of you. Are you around, or I didn't mute you all, no?
Yeah.
I had, so please let me know. It's not like in class, so I cannot see you. Even if I see some of the faces, some of the others, most of the others, I would say, I cannot see you at all. So anything you need to say, please say. I want to have a kind of a feeling like we're in class, so don't be afraid. Or either use the chat or use the or just say something. But don't leave me alone for the whole 1.5 hours or 2 hours, because it's gonna be painful for me and for you. So I don't know if my pace is gonna be too slow, too quick otherwise. So let me know something. Bear with me. Okay, it's 11, so I think I see 25 people. I think I will start sharing my slide. So a little announcement. I'm going to give you the possibility to annotate anything, so please use annotate on the slide if you want to say something, if you want to put an arrow to when we want to do a mechanism or something like that. I will also allow you to share your screens. This is going to be used probably after we use the breakout rooms. Please don't make me regret that. So, okay, let's use annotation and sharing in a good way, okay? So I will start sharing my first few slides. Can you all see that?
Yeah, mate.
Yeah.
Can you all see what I'm sharing now? Yeah. Okay.
Yeah.
So use the bar that you find at the top or at the bottom, or you move it around, and use the annotation whenever you need to. So to start with, this is the new lecture format for this first term. We will see if we're going to use the same kind of format or something similar also the second term. Hopefully not, because if we don't need to use it for the second term, it means that the COVID is leaving us alone. But I have a strong feeling that it's not going to happen very soon. So my lectures are and lectures and workshops are going to be live on Zoom. I'm not going to do anything face-to-face on this term, anything at all. Even the workshops, which we're going to do on Friday, are going to be on Zoom. What we're going to do synchronous, so like we're doing now, is just on Zoom. That means, like I was anticipating, that, well, please watch the videos in advance so that in class it's going to be everything more engaging. That doesn't change much compared to the past years. Please take notes on the videos at home or in class so that you are better prepared or you can engage a little better. Remember that I will make available all the in-class material. It's already on the Canvas, but it's going to be available for you just after each lecture. Anything that is missing, please send me an email and we will fix it. Any questions or more explanation, remember I'm almost always in my office, so feel free to pop in or use the email. A little bit on the workshops. This is a general thing as well. You know that each workshop, also this time, is going to have one assessor question. Since you're going to have the whole day to work them out, I'm not going to give you an idea of what will be the assessor question. So use them and try to solve them as best as you can. And then probably in class, when we have that hour on Friday for the workshop, I can give you some hints on what the assessor question actually is going to be. Because as usual, my idea is that you learn the stuff which is in the workshop. My first goal is not the marking. For you, probably the first goal is the marking, but for me, it's not. So I would like you to use your brain, to use your knowledge, to use the internet during the whole day. And if you all do all the questions on the workshop, is much better. Remember, this is just an announcement which is valid for everything. Everything is work in progress. So like I was saying to you at the very beginning, please give me feedback on anything, how is going the lecture class, the Zoom class, and we will try to fix if something is not working, or we will try to arrange in a way that it works a little better. So the only different thing, since we are not going to have a proper class, is that I'm going to try using the breakout rooms. I'm sure you tried them already in other Zoom classes. I will look probably for today, because it's just a test, I will have only 2 questions, one per part, let's say per video, and I'm going to split you in different breakout rooms. My setup now is going to be 4 or 5 of you, and I will leave Zoom to arrange for the different people in different breakout rooms. I will try and join as many breakout rooms as possible to give you hints on the questions, because remember, we're just trying to learn. So if you don't know how to solve the questions now, it's not a problem. So everything is work in progress, but as I've anticipated, I will allow you to share all your screens and to annotate anywhere. Please don't make me regret that. When I share the slide with the breakout room question, my idea is for you, either you print screen the question. I think the best way, I was testing it, and the best way to me will do a print screen of the question. I'll try to make it more or less at the center of the screen. So then you can open Paint, which is the easiest one, or any other drawing software you might prefer. And then you copy the question and you put the question on the breakout room. So one of you will share the screen in each breakout room, and you will try to solve the question. So I left you the option to annotate anything, so you can use that slide that I'm going to give you, or the print screen that you copy and paste. Please use the annotate with Wacom pen or with your mouse, or use your notes notepad at home. Just the most important thing to me is that you solve the question. So we will learn something out of this lecture. Remember that whatever happens, eventually we will reconvene to the main room and we will solve the question together. So don't worry if you don't know the answer. Then we will do them together, and I will show you how was supposed to be done. Unless some of you, and I hope it's going to happen as many times as possible, unless some of you is going to propose their own solution. So per breakout room, you can save, for instance, whatever happens in the breakout room, and you can repropose in the main room, because I'm allowing you to share. If that doesn't happen, don't worry, because we will solve the question. So general thing about the content of my part of the module. You might have seen on Canvas, we left between myself and Marcella, we left quite a detailed list of topics that we are going to teach. So this one is just the main part. So today, for instance, we will see the a little bit of organometallic chemistry, and especially the aromatic cross-coupling reactions. On Thursday, we will start doing 2 lectures, 2 out of 4 lectures of 2 out of 4 videos. So it's going to be 2 lectures of 2 hours each, basically, on pericyclic reactions and other cyclization. I will do after that a large part, which is going to be other 4 videos and, well, 2 lectures of 2 hours each, basically, on a spectroscopic identification of organic compounds. So this part is going to be really important, especially connected to the labs and especially connected to the research labs that you're going to do in the second term, especially who does it with me or with Marcella or with Joel, because these kind of spectroscopic techniques are very important for any organic chemist. The last part of my lecture is going to be after Marcella's part. So you will have 4 weeks basically with Marcella between the spectroscopic identification and the advanced photosynthesis. In the last part of for me, probably will start early November, I'm going to cover general retrosynthesis. Remember that also Marcella will try to do a lot of retrosynthesis using her stuff, but she does asymmetric synthesis, asymmetric catalysis, and she does a lot of stuff that usually I don't touch too much because I try not to use chiral chemistry or asymmetric synthesis, not because it's not important, but just because Marcella will do. Most important thing is that most of, let's say 80% of this whole course between me and Marcella is going to be based or is going to be used for retrosynthesis. Because in general, retrosynthesis, which you started seeing last year with me in the last couple of lectures, retrosynthesis is basically the hardcore of organic chemistry. Whatever you need to do, first you start with retrosynthesis, and then you propose the synthesis. So the last part with me, the last 8 hours, well, yes, about 8 hours, you won't see much on Canvas because last year I did everything just on the whiteboard. This year, because it's going to be on Zoom, I think I'm going to prepare at least 4 or 5 videos. We will reuse for the first couple of lectures the videos that we used last year, and we will try to solve the problems that you had at the exam last year. So we will use whatever we came up with last year at the end of my lectures. We will use it as a starting point this year. Remember that each part contains more or less at least 1 exam question. So on the cross-coupling reaction, it's very likely you will have 1 exam question. 1 or 2 on the pericyclic reactions because they are very important. Definitely 1 exam question on the spectroscopy. We will have 1 workshop on that as well, and the workshop will be practically the same as the exam question. So I'm always going to put 1 exam question on the big spectroscopic identification of organic compounds because I find it too important. On the last part, as I said, retrosynthesis is the most important part overall of this whole course. So it's going to be 1, probably more exam questions on retrosynthesis, especially if you consider the Marcella will have her own. Okay. So now I'm ready for the lectures, the lecture for today. But first of all, I will stop sharing now, and I want to see some of the faces. Any questions about this first part and the organization of the course? Are you all getting me? Is that the voice, is that the connection good enough?
Yeah, it's really good.
Good.
And good?
Good.
Because sometimes it starts flickering, I know. So anytime, guys, anytime, please stop me, send a chat question, whatever. I don't want to feel alone, okay? You don't want to leave me alone, otherwise I'm too fast. I cover everything, but that means that I'm covering too quickly. Okay? So let's start sharing again. And today I will start the normal way, like I will start in class, with some questions. We will solve some of the questions together. And then at some point, we will try to experiment the first breakout room.
Okay.
All right. So if you watch the videos, the first stuff that we're going to talk about today is all based on cross-coupling reactions. So you saw a little video. I show to all your group a very little short video on the pre-lab for the green chemistry. So the advantage this time is that we did something on the pre-lab. The disadvantage was that you did the pre-lab and you did the lab, and you're going to do the lab report without knowing too much of the chemistry which was behind. But if you watch the videos, you notice two things, that the most important part of the cross-coupling reactions are, well, probably the most important feature is the catalyst. Okay, so all these reactions have to be catalyzed. We will mostly use palladium, but there are so many other more metals, transition metals, and a huge variety of ligands that we use. I do not expect you to remember all the metals and especially all the combination of the ligands. If you remember some, is good. What you need to remember is the role of the catalyst in the cross-coupling reaction and also the role of the ligand. So in this exercise that you can see, if I ask you, if you remember from the video, if I ask you to draw the structure of three complexes which use cobalt as a metal, the ligand in this case is going to be, the first ligand is going to be this cycloheptatriene, which can coordinate different, the cobalt and the other ligand, which is the carbon monoxide, in different ways. So we notice that this eta, this Greek letter, indicates basically how many electrons or how this part of the ligand, in this case the cycloheptatriene, is connected to the metal. Okay, so depending on the different eta, you will have a different amount of electrons, and depending on the different amount of electrons, you will have to satisfy the 18 octet rule, the 18 rule, not the octet like for the non-transition metal. So normally these kind of complex are stable only when they have 18 electrons. You might remember this stuff from probably, I don't know, Simon or Moritz, whoever in organic did it last year. So if I tell you that this is the first ligand that we're going to use, drawn in this way, and we connect the cobalt, I would like to ask you, how many carbon monoxide do you need to add to fulfill the 18 electron rules? Okay, can someone know? Can someone tell me, according to this one, which I'm gonna say, the first one, I can anticipate, is eta equals 3. What does it mean? Anyone?
Do we need 8 more electrons
The
now?
electrons touch the metal.
So how many electrons does cobalt 0 have?
6.
Cobalt 0
Hang
is
on.
the
7,
S2, this
8.
level.
8. 8.
8, yeah,
It's
no.
got 8, yeah.
Let's put 9. Okay. If you look at the periodic table,
Oh, yeah,
cobalt,
actually, is
cobalt
it?
is B7 S2. So cobalt 0 has 9 electrons.
4, 6,
If eta equals 3, it means we have 3 electrons on the cycloheptatriene. So basically, it links in this way. If you remember, this one is like you have a separated allyl. Okay. So in this case, it's linking 3 carbons, sharing. So we will have equal length in all this part. But the most important part for you now is that it's going to have 3 electrons. Now, considering the 9 electrons of the cobalt, how many carbon monoxide do you need to fill it?
3.
How many electrons does any carbon? Remember, I put a table on the video. Carbon monoxide is a neutral ligand, but actually can give how many electrons to the metal? Anybody remember?
Wasn't it 2, I think?
So each one, even if it's neutral, can give 2 electrons. Okay. So
Yeah.
how many carbon monoxides do you need to fill the final structure?
2.
You need 3, right?
So you
You
need 6 electrons.
Yes.
You need 6
Okay.
electrons,
3
but
of
then
them.
you need 3 COs.
Okay. So 3 COs is the right answer. Remember, you count the number of electrons which are on the one of the ligands, the electrons which belong to the cobalt. So there will be 12 electrons. So you actually need 6 electrons. Each carbon monoxide gives 2 electrons. So to make this complex stable, you will need to have 3 carbon monoxide. So what about this one? And the cobalt. So cobalt are still 9 electrons. How many electrons are on this structure if I draw it this way?
Is it 5?
Okay, so remember, just start counting the number of carbons.
Carbons, yeah.
Okay, so you'll have 5 electrons, still 9 electrons for the cobalt. So how many carbon monoxide?
2 now. You need 2 carbon monoxide and 4 electrons.
4 electrons, 2 carbon monoxide, right? So the last one is very simple. The only difference with this structure is that this one has 7 carbons, but if you remember, the cycloheptatriene is aromatic, so it gives you 7 electrons anyway. Cobalt is 9 electrons, so how many carbon monoxide? That is very easy now.
Yeah, just 1.
Just the one. Okay. Remember this one, the cycloheptatriene as neutral as 7 electrons. When it gets aromatic, you need to put it as you need to use it as a cation. And if you remember that, this one, it will be positive. So with positive, we'll have 6 electrons and it will be aromatic. In this case, using it as a ligand, neutral, so no positive, it will give you 7 electrons. Okay, so this is just a quick exercise to just to remember how many ligands do you need to use, especially because if you remember from the video, sometimes, especially in this case, carbon monoxide can be added to the cobalt and it will participate to the final reaction. So it's very important to understand how many electrons are all around, because the 18 electrons is with the cobalt, with the complex when it's stable. But remember that anything that is very stable is not very reactive. If you want a species which is reactive, it must have less electrons. We will see that using all the palladium. Normally palladium, the palladium complexes which are active in solution, they normally have 14 electrons. So they're far from the 18 electrons which make it stable. If it was too stable, it will just sit on the, at the bottom of your bottom flask and will not participate. Okay, remember to count all the ligands. So another thing that we saw was the catalytic cycle. This is something that sometimes I put exams. So knowing a good catalytic cycle and understanding how many electrons and what kind of species are involved is very important. So if we do this kind of exercise, doing this, using this catalytic cycle, wait a second because I need to put my bar up here. Okay, so the typical cross-coupling reaction involves this palladium complex, in this case palladium, but could be any other transition metal, that depends. With some ligand, you need to know how many electrons we need to start with. Then you will have the insertion of your first compound. You did that, you actually did that on with the Suzuki coupling on the green chemistry lab. So it's probably much easier to remember now. Let's analyze just the whole catalytic cycle. In this case, the other reagent is a Grignard. It's not the boronic acid like we did for the Suzuki, but overall reaction is the first halogenous compound, usually aromatic, but sometimes it will be also aliphatic. We normally use for aromatics because it's easier. Most of the drugs contain aromatic species, and the cross-coupling reactions are very good to make new aromatic compounds. So in this case, we are mixing these two species, and we want to see what we obtain and each part of the catalytic cycle. This one could be easily an exam question. Okay, so as I was anticipating, normally the palladium 0 comes with 14 electrons, which has 2 ligands only. Then the first, remember the first reaction, what is called?
Oxidative addition.
Yeah.
Okay, so you obtain this one. This one is an oxidative addition. So in the exam, you will write the whole complex here. and you have to specify that it is an oxidative addition. As you can see, basically, like I was showing in the stupid video on the YouTube, basically the palladium insert here in between the two. I don't know why do I have sorry. I'm messing up with pen. So pen again. No, I still have this stupid. Anyway, let's do this way. 16 electrons. So what happens here is that the palladium gains 2 electrons because we start from this palladium complex with 2 ligands. Now we have 2 ligands, extra ligands. In this case, you're going to take 1 electron for each one. So you're going to end up with 16 electrons. I still need to find out why I have the eraser instead of the. Okay, got it now. So 16 electrons here. So then this one will be the transmetallation step. Okay. Yeah. What happens in the bottom one? What happens here? What do you expect?
It will be R dash palladium, R double dash, and ligands above and below.
Well, what do you need to know, apart from all the different bonds? Look at this step. You have 1 metal here, so it's literally a transmetallation. So basically, this R moves from this metal to the palladium because it's more stable. So you will have the 2 sides that eventually you want to link in the same complex. Okay. So the palladium still has 16 electrons. So what happens here? What is the next step?
Reductive elimination. Okay.
Before the reductive elimination, do something else.
There's something else.
Okay. So this one, it will be a trans-cis isomerization. It's not that important from the chemistry point of view. From how do you picture? But actually, this one are trans. They normally get closer to get into cis, so that they are closer to each other to do the final step, which is like I think Albert was anticipating, the reductive elimination. Okay.
Lino.
Yeah.
Where's the X come from after you do the trans cis? Is that a mistake or is that actually added on?
This one with this one, it goes out. It goes out eventually as
where did it?
X ligand. Look at the. You need to restore the palladium complex because the palladium is a catalyst. So this one needs to go back in solution. Okay.
Where does that X come from? Is one of these ligands an X?
Okay. Here, eventually, you will have one LX. So,
doesn't it?
Okay. You see that here we have 2 ligands. Here we have only 1. We have to restore the second ligand. So this one goes out in this stage as a ligand halogen. And after the reductive elimination is taken again by the ligand is taken again by the palladium to restore the catalyst because you need to use catalytic amount. So this one, the palladium 0 complex has to restore with the 14 electron so that it goes back and acts as a catalyst again.
So is the X taken by the magnesium here and then put back on here?
Well, potentially, yes. Or also, you remember there was an X here. Here you remove this X first. So at this stage,
Yeah.
the magnesium with the other, it could be, if it was a grignard, this one will be a bromide. It could be another bromide. The bromide is, it could be, this one could be basically magnesium dibromide. Okay, so basically we'll have two bromides. This is just a typical example. I didn't want to go into that details, but since we are using it, the ligand could be a phosphine, and the phosphine can take one of the bromide, which was around here, and then eventually he has to go back into the cycle. Remember that, for instance, in this specific case, if we had a magnesium bromide, this the grignard gets destroyed. So eventually, at one sequence reaction, you will have either magnesium bromide, or you will have, if you quench with water, magnesium hydroxide. But this is specific. What I wanted to focus on this one was the palladium catalytic cycle. But yes, they're all good questions, and it's good to know. In this case, if it was an exam, I will literally ask you for all these 4 steps, and for instance, the structure of the palladium at each time, and the number of electrons of the palladium for the palladium at each time. Okay. Any other questions on this one? Or you will see the most of them are similar. So use the Claydon, look at some others on Google. Most of the palladium complexes, most of the transition metal, actually, the catalytic cycles are like that. Then sometimes you will see extra cycles or rings over rings, because there is maybe another catalytic cycle which involves, for instance, sometimes it involves the other component of the reaction. So sometimes it's catalytic also the other metal which is being used on the transmetallation. But in this case, we are going too much in details, and this is not the focus on my part. The focus on my part at the moment will be how to make, in the end, will be how to make from this one, from this one and this one, the coupling between the two R groups. Normally speaking, what I would like you to use, especially from the retrosynthesis point of view, is aromatic. So if you see in any of the retrosynthesis questions, if you see a bond between an aromatic and another aromatic, try to think immediately, I may use a cross-coupling reaction in synthesis later on. So the retrosynthesis will break the bond here, and you need to indicate the 2 parts of each of the 2 components of the 2 reagents on the synthesis part. Sounds good? Because in the end of the day, yes, we are trying to get the mechanism, but the whole part, my part and Marcella's part, is on retrosynthesis. So it's focusing on retrosynthesis. So I want you to learn how to take a large molecule in the end and split in so many different parts, so that if you're going to the lab, you know where to start with, going down with smaller molecules, so maybe commercially available, and to use them to create much larger molecules, let's say a drug. Okay, so this is the main focus on each part of this course. Also, both the cross-coupling reactions and the pericyclic reaction in my case. Okay. Any other questions on this one? We will see others. So we will recap on the catalytic cycle. Okay. So now let's try to do the breakout room. You're all happy with the exercise. This one is very easy. I think I'm going to give you something like 5 minutes in the breakout room, and you will try to solve all this one. What I would like you to focus on this one is, where does the palladium insert and what happens? Okay, so what will be the oxidative addition step in each of these potential complexes? Okay, you all happy to take notes of these structures, or you are going to try the print screen and then you share into the breakout room? What do you prefer, guys? So if you are taking notes, please let me know when we can split into breakout rooms. Okay. It might be longer than other today is just a test, so it might be longer than others, but I would like to try the breakout room thing.
I just got a screenshot mine at least, so.
Yeah, you can screenshot with your mobile. You can take notes on your pad, or you can do literally a print screen, open Paint, and try to do to copy and paste basically the print screen. If you copy and paste the print screen, you can then share within your breakout room, and then you can solve the exercise annotatively. I'm going to split you in breakout room now. I will have 6 rooms basically, and then we'll try to join each breakout room. Okay?
Yes,
Let's do it in a more or less 5 minutes. So now you're all invited to join each breakout room. Okay. So now I am with you in the first breakout room. Can you hear me, yeah?
Yep.
Yeah.
So what's your plan? Are you going to share the screen, or you're going to discuss? What I would like you to do is try to solve any kind of exercises like that. The one that I have for the second hour is going to be very different from this one. So what do you think? What do you think happens here? So first of all, you're using a palladium source. So I'm not asking you for any ligands, whatever. You can just write the palladium, and you should tell me. I've anticipated this an oxidative addition. So which of the 2 halogens in the first one gets that palladium? I mentioned in the videos normally.
Is it going to be the bromine?
Why the bromine?
Because it's going to be more likely to be oxidized than the fluorine.
Well, technically speaking, yes. So that's a good answer. Also, the bromine, the carbon-bromine bond is a lot weaker than the carbon-fluorine bond. So if you have to do an oxidative insertion or oxidative addition, basically you are inserting the palladium here. I don't know if you can see. You cannot see my annotation.
Might have to allow you to.
Okay, so if it goes into this one, you have to break a carbon-fluorine bond. It's not easy. Carbon-bromide bond is weaker. So what happens in the first one? So what will be the final structure?
Let's pretend that's a fucking.
That's why I thought, okay, the Wacom pen is actually very useful. But I help you with the palladium, I guess. Good.
And then that would be PD.
PD2.
Yeah. And then remember, you need to add the bromide on the other side as well. Okay.
Cool.
Okay.
Oh, I see.
So what you need to remember is always the palladium inserts between the carbon and the halogen. Always. Any oxidative addition works more or less this way. Okay. It must insert the palladium, or the transition metal has to insert in the bond between the part that you want to couple and the leaving group. as usual, bromide is also good because being larger is also a much better living group. Okay, I'm going to leave you this room and I'm going to join another one. Please do the others.
Hello.
Oh,
Hi.
oh, I.
Hello.
Let me get off annotation how.
Okay, then. If that's done, let's move on to the next one.
Show names of annotators.
So for this one,
Okay, guys, so this one works well. And try to do, just quickly, because we will reconvene in the main room because I give you only 5 minutes.
yeah.
We need to be quicker next time, all of us, me included, actually me first. So where does the palladium go? Between which bond in the second one? Which one is more likely to get?
Iodine,
Why the iodine?
because it's like further down the group and they always leave.
It's the most
Okay,
reactive
so
one.
your normally goes in the larger one. Okay,
Yeah.
carry on. Yeah, it's almost finished. Okay, how are you guys? That's good.
Hello.
What you need to know now is why between the carbon bromide instead of the carbon fluoride.
The bromine's more reactive in this case, right?
It is more reactive. The bromide is larger, so it's a better living group.
Yeah.
And the bond between the carbon and the bromide is much weaker than the bond between the carbon and the fluoride.
Yeah.
Okay, so that doesn't change much compared to the reactivity of other carbon bromide bonds, especially attached to aromatic groups. So consider that in the second one, where does it go?
Go on to the iodine.
Okay, so it goes to the iodine for the same reason. If you have to choose between iodine and chloride, clearly goes to the iodine. If you have to choose, if the other one was a bromide, there will be competition. Because it might go to the iodide anyway, but there might be some competition between the two anyway. So you will have a mixture of products. But in this case, the magnesium, like in this case, you're forming a Grignard, basically, it goes into in between the carbon and the iodide.
Yeah,
So the insertion, it's always good. The insertion is always this one, always this one. Okay, so that's correct. You keep the other two ligands, if they were ligands. I say just a palladium source. Sometimes I don't care about the number of ligands. To me, the most important thing is that you remember this part. Okay.
Okay.
Go for the last one, but I think we have to finish the breakout room.
Okay.
Then we will talk about now.
All in quarantine. That's a noise.
Yeah, I came up to Swansea for a couple of days and I was like, I don't need to be here. I can drive in once a month for my labs. So I was like, fuck it, go home.
So all the breakout rooms, guys, now are going to close in 50 seconds. So you're more, half of you is already here. So quick thing, how did it go with the breakout room? Do you think you can carry on, or it's too slow?
All right, apart from Ellis, because you didn't put Ellis in a room.
Yeah, you didn't put me in one.
Great.
Yeah, it was fun. It was fun. It's good.
Yeah,
so we will do later for another exercise, which is going to be completely different from this one. Okay. I want to know if you're happy to carry on with a couple of exercises in breakout rooms per lecture.
Yeah.
Do you think it's? Yeah. I will say at the end if I'm going to cover and I'm trying to cover all the material as much as possible. Remember that again, you will have all the exercises and all the slides on Canvas after the lecture, just straight after the lecture. So whatever you think you missed is going to be on the slide. If it's not on the slide, or if for any reasons something goes wrong, remember, just email me or Marcella if it's Marcella's part. Give me a second because I need to put the charger on my laptop, otherwise I will lose you. So I've seen only, I think I've seen 3 breakout rooms only. Did you all get the print screen and did you start annotating?
Yeah.
Yes, I grouped it. Yeah.
With the mouse, it's not as easy as with the pen, but I'm pretty sure you can do. Everybody needs more practice on this one, okay?
Yeah, just more practice.
Yeah. So now let's carry on with the rest of the slides because otherwise I'm going to be too long. So can you all see this new exercise now?
Yes.
This is a more difficult exercise, okay? But this is, you are doing organic chemistry for the 3rd year, so you expect to have a difficult exercises. So here you have the solution already, and I can leave that to you. We'll see on the next exercise without the solution. So what I will ask you to do here is, this one is an exercise straight from the Claydon. Claydon doesn't make very easy exercises, but they're all very good. If you can do the exercises from the Claydon, I am pretty sure you will do very well all my exams and Marshall exams. So in this case, you have the palladium with a triphenylphosphine, triphenylphosphine tetrakis. So it's a palladium 0. You will have the possibility of, whenever it's a Heck type of reaction. So in this case, you will have the possibility of linking either one or the other ligand. You can see from the solution here that if there is a chance at the beginning to link straight away a double bond, the palladium probably prefers to coordinate the double bond right here, okay? So what happens there is that, like we have seen in the first part of the lecture today, this one usually coordinates as an allyl, okay? Because it's more stable. What happens next, what I will ask you to do is to tell me what happens in each step. So after the first coordination, you can imagine that in order to reach the first example, the first part, so that is going to be, let's say, the first part of the exercise, or could be the only part of the exercise on exam, because this one is difficult enough. So what happens then is that once you link the palladium in this way, then you can link the other one. If, like for every other kind of organic chemistry reactions, if you see a structure and you know that you need to use the reactivity of any of these carbonyls, for instance, in any possible ways, let's always remember the potential enolate, okay? So instead of using the carbonyl, you can transform into the enolate here. And then if you know that at some point you will have to do the coupling of the palladium with the other double bond, this is what happens. This is what happens in the actual reaction. So you wait until it forms the enolate, then you get the double bond. Then at some point, the palladium usually likes the double bonds, and then you can end up with the structure after the reductive elimination step. Now, since we are always talking about the reactivity from the organic chemistry point of view, even if it's not a cross coupling, any idea how to pass from this one to this one? What would you use? Because this could be another part of, let's say, an exam question. So you need to reach from this one. You need to reach this one. What do you use to transform this one into this bromide? And if you remember, okay, for the sake of time, I can show you this one. Okay, so can you see how it goes? Do you remember what this one is? Remember the name? of this structure. Have you seen before? This is a brominating agent. It's called N-bromosuccinimide. Normally known as MBS. It's a very good brominating agent. So what happens here is that this bond between the bromide and the nitrogen is very weak. So it can be attacked by the double bond. In this way, you kick out the ethyl group from here, and then you get the bromide. So this is a typical extra step that is not concerning the cross-coupling reaction in this case, but I always like to connect everything with another potential question on retrosynthesis. Okay, because it's not just important the cross-coupling part that we are doing today, is how to use this cross-coupling part in a proper retrosynthesis exercise. Let's say that I wanted to do, that will be a difficult one, I'm anticipating, but let's say that this one was the target molecule and I wanted to ask you, how do you disconnect this one? The first disconnection will be the extra step which comes later. Okay, so the cyclization. I need to, okay. So if you have this bromide and this carbonyl here, you can imagine a Wittig reaction, okay? So you can transform the bromide in the phosphorus halide, like this one, and then the phosphorus halide can be easily attacked. The carbonyl can easily attack the carbonyl in this way. So what you need to do from the retrosynthesis point of view, for instance, will be to break this bond first and imagine it comes from the Wittig. So from this part, and then the carbonyl and the bromide. Then all the rest could come from the reaction of the bromosuccinimide with this ester. Kind of an ester, it's not an ester. This alpha beta unsaturated compound. And then what is important for us today is that this one can be broken in retrosynthesis. From the retrosynthesis point of view, can be broken here. And you can get the first two parts, which they actually come from the cross-coupling reaction. Are we okay with this exercise? I know it's complicated, but we have to start tackling complicated exercises. Can you see all the steps, both in synthesis and potentially in retrosynthesis?
Yeah.
Yeah.
You sure?
Yeah.
Because this one is a difficult one, I'm telling you. But in each time, if you see complexes like that, or complex molecules like that, try to break them into smaller molecules, starting always from the weakest bond. Okay? Or initially, you can cut this one because you know a double bond. If you see a double bond, it could come from dehydration or it could come from a Wittig. In this case, it comes from a Wittig reaction. If you use the Wittig reaction, you open the first cycle. Cyclization in terms of synthesis will be very easy. The difficult part, probably the most difficult part of this exercise will be spotting that this part can come from the cross-coupling reaction using a palladium catalyst. Let's remember something else, guys. Like I've anticipated last year on retrosynthesis, there are more than one good solution. So if using the same kind of molecule, you use a completely different technique, completely different retrosynthesis and synthesis, and you come up with the same good solution, I'm very happy for you. And I will give you all the marks. Okay? So this one I need to, so this is the bad part of the, I don't know why, it kept these two. Never mind.
You can click the button clear, it's like a picture of a trash can over to the right.
I can do annotate, but if I clear, okay, now I cleared everything. Thank you very much, Willie. Because last time that I tried on my test, it didn't work. So I noticed that sometimes I can leave some of the leftovers. Thank you for that. So this exercise, can you all see the top part? This is another difficult, but it's not as difficult as the previous one. So if I tell you that on this X-style reaction, with the Heck, remember, with the Heck reaction, normally you use a double bond, a palladium catalyst, and eventually you keep the double bond. So you might imagine that this is the product that you should end up with on the next reaction. Actually, I can tell you that this reaction doesn't work. Can you imagine why it doesn't work?
Maybe like steric hindrance or something.
Not exactly. Not exactly. Do any of you remember from the video what is probably the most important part of the Heck reaction, apart from the, of course, the oxidative addition and the reductive elimination? There is an extra part which is very peculiar and typical, and is very useful for the Heck elimination, for the Heck reaction. Anybody remember what is the driving force of the sometimes of the Heck reaction?
Is it the elimination, the hydride elimination?
Exactly, the beta hydride elimination. Okay, so on this one, I can tell you, we'll do quickly after the first oxidative insertion, oxidative addition. So you will have the first one. Then what happens here is that there is no beta hydride on the aromatic part. Okay, so this one doesn't have a beta hydride. So it cannot eliminate to restore the double bond and to form this double bond. So what do you think happens, considering that you know already what is the correct product instead of the double bond one?
So is it a hydride shift? Is that what it is?
It's not exactly a shift. Focus on this part. Okay, basically this hydride is already there. You don't write it, but this hydride is not already there. So nothing happens here because there is not a beta hydride available. But what happens here. So you substitute this one with an extra hydrogen, because in this one you will have 2 hydrogen. And this is why, if you read the whole question, you find what is the purpose of the formic acid. It's not to cure out of the formic acid. I'm pretty sure if you use acetic acid, it will work the same. The most importantly, you need an acid. What do you need to do? Basically, you just need to decompose the palladium complex. Okay, so this is what happens. Okay.
So in the second step, Lino,
Yeah.
so you've got the one arrow coming from the PD carbon bond going to the hydrogen, and then is the other arrow going from the bond to the carbon?
Can you indicate exactly what arrows are you talking about?
Yeah.
You can annotate.
It's like this one here, this arrow that I've just colored in. Is that showing like this carbon to hydrogen bond forming that you see in here? Okay.
Yeah.
Just
so this
it
one
looks like
stays.
it's kind of going back to the palladium.
Yeah.
Okay.
So this one stays because at the beginning, in this part, you will have a hydride here. You have this hydride already. Only it cannot participate to form the double bond. So what happens is that you quench the reaction with the acid, and this is what happens. So basically losing completely this part of the catalyst and forming the saturated version instead of the double bond version. So it is an Heck reaction technically, but in actual fact, from all the Heck reactions, you expect to find a double bond at the end. Normally, if you want to remember the difference between Suzuki, Sonogashira, Heck, I will never ask you, do the Heck reaction. But you can individuate, for instance, if in a retrosynthesis there was a double bond and an aromatic coupled, you can imagine this one may come from an Heck type of reaction. Only you need to do, once you do the retrosynthesis, and for instance, you will disconnect in this bond, saying that this one comes from a Heck style reaction, you need to do in synthesis all these steps, and you should individuate that this one actually will never keep the double bond. So that is the extra level of difficulties on the retrosynthesis reactions, because on the retrosynthesis, you can do basically whatever you want. As long as you separate the charges, you put, like we've seen last year, a symptom plus and a symptom minus. Technically speaking, you can do whatever you want. So on the paper, you can do whatever you want. But then you have to imagine that if you go to the lab, you need to mix the two reagents. And you have to know also that if you mix these two reagents, instead of getting the double bond, you will get the saturated one. Then maybe there is a way to create a double bond from here, but this is something more difficult. This kind of hydrogenation is not part of my course. Okay? It's midday, so I don't know if we want to do a quick stop or we carry on. What do you prefer?
Can you go back for like 2 seconds, please, Luno? Like literally at 2 seconds.
Back on this one.
Yeah. Sorry, everyone else. Okay, yeah.
Remember, this lecture is going to be recorded, so you can go back and watch all the different steps. But also, I will leave you all the slides in Canvas. Okay. So apart from my annotation, but the annotation is basically scrubbing everything on here, like we were on the whiteboard in the lecture. All the apart from the annotation, you will see all the different slides and all the different steps on Canvas after this lecture. Okay.
Yeah, I'm good now, but thanks.
Okay, so this one, we'll do quickly maybe this one, and then probably we'll stop. Let me check. Probably we will stop maybe for 5 minutes, 10 minutes, it's up to you. And then we'll carry on with the rest of the lecture. So on this one, let me check if I can remove more drawings. Yes, okay. So considering that, what we know, what we've seen on the video, using this kind of compound, I can suggest you this kind of ligand as well, and a palladium catalyst. How do you make this lactone? Any ideas? What do you think will be the role of this carbon monoxide? If you remember the first video, there was a particular step that sometimes is helped by the addition of a ligand. In this case, it's very useful, and it's useful very often in synthesis. Anybody remember? Anybody remembers that migratory insertion? Sounds familiar?
Yes.
Okay. So.
Oh, I see.
Every time. So the first step will be insertion of the palladium as an oxidative addition. So this is the main part, always. The first part is you start from your bromo compound and insert in the bond between the carbon and the bromide in this case. Okay? So the palladium inserts here. It gets palladium 16, palladium 2 with 16 electrons. But what happens here, and this is something that you may want to notice, every time there is carbon monoxide, is a very good ligand. And the ligand, sometimes it either replaces other ligand or inserts. So the first part will be the addition of the ligand because, as I said, carbon monoxide is a very good ligand. So it has to the ligand replacing one of the other ligands, whatever the ligand is. Let's say it was a triphenyl phosphine. But then what happens here is this migratory insertion. So basically, this one moves as it was a carbon ion. It moves around here, like it was, you can imagine, in a similar way as we normally do with the carbonyl. So this one moves to create a migratory insertion and to create, wait a second. Eventually the lactone. Can you see that? So the migratory insertion goes here. So first reaction, oxidative addition. Okay. Then there is the ligand addition, because first it adds, as soon as it adds to the palladium, this large aromatic moiety moves here, like you have seen probably all the rearrangements with Joule. Is that this kind of migration is very typical of several rearrangements. This one, you can see it as a rearrangement as well of the molecule. What you need to remember is that if you're using carbon monoxide, there is a huge chance that eventually you will end up with a carbonate. Okay? So what happens here after the migratory insertion? So basically, this one is being inserted between the palladium and the aromatic moiety. What happens next is this oxygen, you have this methylene connected to the oxygen, is an intramolecular cyclization, so normally it's easier. So the double bond of, the lone pair of the oxygen can easily attack the carbonyl because it's very close. So the entropy is totally in its favor. And eventually you get rid of the palladium part, forming the lactone. Can you see that? So this is something that if I ask you from the retrosynthesis point of view, it will be mildly difficult to spot. Because if you do a normal retrosynthesis, even if I do a normal retrosynthesis, I will think about breaking here and getting instead, okay? It's difficult to imagine this part. But if you remember that and you're clever enough, you can imagine that this carbonyl might have come from oxidative insertion, migratory insertion on this molecule. As I said, it's complicated, it's more difficult to see, but again, we are doing organic chemistry for the third year, so I'm afraid something is everything more complicated. We'll do a break, something like, let's say, 10 minutes, and let's come back at 12:20. We'll finish before 1, I promise you, okay? Everybody happy?
Yeah.
Yeah.
How's it going so far?
Can you remember it?
Gucci, can you remember it if I gave him him?
I remember it. It's about a clown in Derry.
Clap.
Okay, I don't know if I want to ask really, but why the two brothers are upside down now on my screen? Did you do it on purpose?
We're in Australia.
Really?
Ever I'm in Ibiza?
Oh. Okay,
no,
guys.
I just flipped the camera.
Just for the fun of it.
Yeah, just.
Okay, guys, I'll give you. Let's go back at 12:20. Let's do the last part of this.
That's time to make
lecture.
a sandwich. Yes.
It really is. It's a good shout, Mitch.
Yeah, let's fucking go. Should I bring you guys along with the journey?
If in the meanwhile you have any questions you want to ask me when we rejoin everything, please ask me or send them in chat by email or anything, okay? I'll see you in 10 minutes. Oh,
Today's lecture is sponsored by Pringles.
Middle.
For crunchy goodness.
Is that Nor? Hi, Nor.
It's not.
Australian Pringles or normal Pringles?
Australian Pringles. They're upside down.
Okay, I can see now. Yeah.
Yes. But we're sponsored today by Pringles.
Assalamu alaikum.
How do you guys find the Zoom lectures instead of the normal one?
I went and got a cup of tea, which is rare during a lecture, so that was nice.
Yeah, because I don't particularly like them, to be honest. Too much Zoom. I don't like. The point is that Simon offered to do some face-to-face, but I think that the risks at this period are still too big, and I try to prevent any contact as much as possible. Not to me. Not particularly worried for me. I'm more worried for giving any extra chances to spread even more this stupid stuff. Probably should be avoided. That was my idea. So I decided that both, at least Marcel and I, on this part, on this third year, on this module, we're not gonna do face-to-face. I know it will be so much better because I always enjoy that.
You just did that so quickly.
I'm very sorry about that, but maybe the situation will get better. Who knows? And maybe in November on my last part on retrosynthesis, I would really like to do it face to face, but we'll see how it goes. And if I have to do something face to face, I prefer lectures over workshops. Workshops, pretty happy to do them on Zoom.
Looking it up.
Not gonna lie, I don't think many people just come in for an hour at 11 a.m. No, 2 p.m. and 5 p.m. on a Friday to come into a workshop.
Yeah, I imagine those hours are horrible. We'll have a lecture. Probably the lecture on Thursday will start at 5. So I always try to make it as short as possible, but I know that people is pretty exhausted by the time. But this is the situation that we have at the moment, so we have to keep this way.
Oh, Lena, you're our year rep, aren't you?
Yeah.
Is Deb about? Because we've heard nothing from him. We meant to have a lecture at 5 with him, and we've heard nothing.
He's not in today. I didn't see him, but hopefully we'll be on Zoom. I'm pretty sure we'll be, because we had a meeting last week and everybody was happy to do all the Zoom links. Do you have a link from him for today's lecture?
No, none of the contents on Canvas, nothing. So
I will investigate. I will ask Simon later, and I will investigate a little bit, and I will let you know.
Cheers.
Hopefully you'll know by the end. Very soon. What time are you supposed to start with him?
5.
5. Okay. I'll ask around. I'll try to speak to Simon later on because I'm in the office.
Thank you.
Another quick thing. Tomorrow we have lab with 21 people. Do you know who is going to come tomorrow and who is going to come? The other 7 who is going to come next week, or we have organized later.
We have a list. Do you want me to send it to you, Lino?
Okay. No, I wanted to know if Simon gave the list to you. I'm okay.
Yeah, we've got it. Yeah.
Okay, so you'll know who is coming tomorrow and who is coming next week on the Innolate Lab. Okay, that sounds good to me.
Yeah.
If everybody's here, maybe we'll restart. We will have only one flip. What is that? Okay, Mitch, get out. We'll have only one breakout room, another exercise on breakout room. If everything goes smoothly, maybe for next time, we will do a little more breakout room questions, but only if it doesn't get too long, because I don't want to keep you longer than I actually need and you want to. Okay, so I will start sharing the screen again, and then once the breakout room question comes, we will split probably in the same breakout rooms. Okay.
Okay.
So for the moment, okay, can you see? Can you all see the top part of the question? Otherwise, move the bars around like I'm doing. Can you all see the question here?
Yes, Lima.
Yes, thank you.
Okay, because on this one, what I would like to do is not too much using the cross-coupling synthesis, which is going to happen anyway, but to start with, because we're always talking about retrosynthesis, so before starting from this one, what is important is that in this case, we're talking about a Suzuki coupling. Like we said before for the Heck reaction, in which you normally expect to retain, in a way, the double bond. All the Suzuki coupling, you can imagine starting from any kind of boronic acid, okay? The point is, you also, if you were in the lab, and my final goal is, again, is always that you come to my lab and you say, okay, I need this boronic acid. Maybe it's not commercial. This one particularly is commercial, but it's not commercial. How do you think you're going to make the boronic acid? Any idea how to make a boronic acid so that then you can use it for a Suzuki coupling, like in this case? Anybody knows? Any hints? From the silence, I take it as a no.
Yeah, no,
So,
sorry, Lima.
that's okay. Now, let me change it as well. So, any boronic acid, if I ask you on retrosynthesis, might come from, remember that this is the most important part of the Suzuki coupling. Without that, or a derivative, so this one is a proper boronic acid, but not always use this. You use this boronic acid specifically. You might use any boron complex, okay? So this one, for instance, might come from the Grignard reagent and this commercial available boron suppliers, let's put it this way, okay? So in the retrosynthesis, you will break the bond here. What you need to remember is that if you use a Grignard, you actually starting from the bromide. So this one is bromoanisole. That's what this one is commercial. So this one, even if it's commercial, can come from the bromination of the methoxy. What you need to remember here is that if you do the bromination of the methoxy, it may go either here or here. Of course, the equivalent part. So in retrosynthesis, you might end up mainly with the para substituted bromide because the bromo is quite big. The methoxy is not as big as the bromo, but it's large enough. So technically, these two positions are a little more hindered. So normally, most of it goes in para position, but you expect a little bit of ortho substituted as well. Then if you want to go for the methoxy, this one is anisole, super commercial, doesn't cost much. But on the paper, like we did last year, you can start from phenol. So the one that you see at the bottom, like I will ask you for any kind of retrosynthesis, is normally coupled with the synthesis. So this is the forward synthesis of the boronic acid. So starting from the beginning. So the last part of retrosynthesis is always the first step in synthesis. So you start from the phenol, SN2 to create anisole. One equivalent only because you'll get a 10% of ortho-regioisomer. Do you remember, or you have any idea why I'm suggesting one equivalent only of bromide, or bromine actually? Do you remember why?
Avoid multi-bromination.
Yeah.
Exactly.
Exactly.
Why do you think multi-bromination might happen here? So think about this molecule.
Because it's favored or favored.
So what is this one? Electrodonating or electrowithdrawing?
I think it's withdrawing.
No, the methoxy is strongly electrodonating. So electrodonating gives a lot of electron density to the ring. It makes it more electron rich, so it makes it more prone for electrophilic aromatic substitution. And this bromination is exactly an electrophilic aromatic substitution. So if you have anything that helps the electrophilic aromatic substitution, you either use one equivalent only of bromine, or you use another brominating agent, like we have seen the N-bromosuccinimide before. It gives you exactly one bromine. But most importantly, here in this kind of electrophilic aromatic substitution, or if you want to remember, it has a Friedel-Crafts-like reaction. But technically speaking, is a proper electrophilic aromatic substitution. You are supposed normally to use a Lewis acid, let's say aluminum trichloride. If it's very activated, you use one bromine only, one equivalent. And also remember, do not use, if you are in the lab, do not use the Lewis acid if it's very activated. So this reaction gets the bromide, so the bromoanisole, with a little percent of the orthoisomer, like I was saying before, but especially you don't use high temperature, you don't use aluminum trichloride, and you try to minimize the multibromination, okay? After that, from the bromide, you can make a Grignard with the magnesium. You can also use lithium so that you can create the lithiated reagent. They are pretty similar. We have seen them both. They both have a strong negative charge on this carbon. The most important part is that then this negative charge can attack this boron, because remember, boron, in this case, this one, is electron poor. So it really would like to, it doesn't have the octet, it really would like to accommodate anything to fulfill the octet. Then, once you create the first complex, so the negative charge attacks the boron here. You create this complex, and then simply with a dilute acid, you create a proper boronic acid that eventually you will use in the Suzuki coupling. Okay? Happy with that? I will always try to mix up whatever the topic is with some extra retrosynthesis steps, because we always aim for having as much as possible retrosynthesis, right? So what about this one? Once we created this boronic acid, we have to do the Suzuki coupling between these two. The reaction is pretty similar to the one that you did in the green chemistry lab. So can you do the catalytic cycle on this one? Do you remember now? Hopefully you can fill all of them. Remember, the most important part is that at the beginning, this palladium 0 has 18 electrons.
Yeah.
You need to lose 2-phosphine, triphenylphosphine ligands to create the 14 electron palladium complex that is actually active as a catalyst. Right? So the next one, if this is an exam question, you need to know where to put the first reagent on the for the oxidative addition. Then again, this is what happens. So sometimes we can indicate the two ligands in this way. It's not that important. We have seen the cis-trans isomerization on the other one. Sometimes it's so quick that you don't even need to mention it. So what you need to know on this one is this one. Again, the palladium has, let me take this one, has again 16 electrons. Then the next step is the transmetallation. So if you see the boronic acid, boron is almost a metal, is a metalloid. So it's not considered a metal, it's not considered one of the typical organic elements. But in this case, for the Suzuki coupling, the boron is used for is basically for a transmetallation. So what you will eventually end up in the next step with this compound, and of course, cutting the catalytic cycle a little short, you will end up with these two moieties. So these are the two molecules that you want to mix together, okay? So important step here, again, this one has 14 electrons, it gains 2 in the oxidative addition, then the transmetallation occurs. The transmetallation involves the boron in the Suzuki. You create this one as a byproduct. Then you end up with this complex. You still have 2-phosphine. In this case, you simply do reductive elimination forming the final molecule and restore. Remember here, you will restore basically the palladium bis triphenylphosphine complex, which is this one, which goes back in the catalytic cycle. So that's why you normally use less than 1% of the palladium complexes as a catalyst. You saw that in the green chemistry lab. This lecture was nice to be done before the green chemistry lab, because then you might have appreciated a little more also the very teeny tiny amount of palladium complex that you need to use for that reaction. In this case, we are doing as a sort of retrospective lecture, okay? So you did the reaction first, and we are explaining why did you need such a small amount now. Everybody happy with this one? This is just another typical catalytic cycle. And this is something that it may always come up in lectures and workshops. Any questions? Questions, guys? No? In this case, we'll carry on. This is a difficult one, again. I love some of these exercises because they should stimulate your imagination. But this one is a Negishi coupling, sorry. Okay? Can you see what happens? Remember, the Negishi normally can use zinc complexes on this side. And the Negishi is pretty similar in the end of the day. It's something in between. If you want to see it, it's something in between the Suzuki coupling and the Heck coupling. But actually, it typically uses the zinc complexes as well. So, what happens? This is the final step. You can see that because of the zinc complex here, you retain the double bond. So that part is similar to the Heck. But actually, this typical carbon-carbon formation bond is very typical of the Suzuki as well. So it's something in between. This is the catalytic cycle. We are not going to do it, all of it again. But this is just, again, 14 electrons here, 16 electrons there. In this case, the transmetallation, which is a very important part of the cycle, the transmetallation always occurs in the presence of zinc. This is the Negishi. So there is, from the retrosynthesis point of view, if you need to use it, there is not too much difference between the Suzuki and the Negishi. One of the differences is that if you do the Negishi, you need to create the zinc complex, but you don't start with the boronic acid. So that depends on the other part of the reagents that you're going to use it. Or in case of retrosynthesis, if you start from here to there, you know that if you break here, if it was a Suzuki, you can put a boronic acid on this part. If it's a Negishi, you can put a bromide straight away. But if you want to do a Negishi, you need to tell me that you're going to put the zinc complex as well. Okay, now, let's try again. This is a completely different question from before. Let's try again in another quick 5 minutes in a breakout room. What I will ask you is, list 3 reasons why the metal ligand coordination complexes, like we have seen so very often, palladium tetrakis triphenylphosphine, or like you did in the lab with the palladium acetate. They're often very useful, more useful than using, for instance, the metal itself. So you can imagine using palladium 0 like you use the magnesium in the Grignard. But normally palladium 0 is too little reactive. So you use ligands, and there are several reasons why you use ligands. What I would like you in this next 5 minutes in the breakout rooms is to think about, to come up with 3 reasons why these ligands are actually very useful in combination with the transition metal. Okay, I will split you in breakout rooms again. I will try and join you all the rooms as many as possible, and I'll see you back in 5-6 minutes. Okay, you all got the questions, yeah? So try to come up with 3 reasons why you need the ligand connected to the palladium or to the cobalt, to the nickel, to any transition metals instead of using them like you did, like you use the magnesium. I'll see you in the breakout rooms.
Hello, Lena.
Hello. So, came to you because I didn't see your breakout room previously. How's it going? How is the breakout room experience? Does it help or it hinders?
I think it will help because we get more chance to like talk between each other
Yeah.
and discuss things. So.
That is the main idea. So I hope you enjoy it, and let's make it useful. So can you imagine of any reasons why?
Okay.
So it's probably like because you can change the, I don't know how to like put it into the right words, sort of you can make the metal, the metal more like suitable as a catalyst, I guess, for like
Yes, absolutely.
reaction.
This is one of the reasons.
It's like based on what substituents you have.
Yep. We saw it like we did before. This palladium tetrakis triphenylphosphine is actually quite inert as it is. But if it loses some of the ligand, then suddenly the palladium becomes more active. So the presence of the ligand and the possibility for the ligand to dissociate from the palladium makes it a good catalyst. So this is one of the good reasons. Any other possible reasons? There is a very general one. If you think about, as I said, consider what you do. If you remember, what did you do on the Grignard reagent? You use magnesium metal. Magnesium metallics usually needed something else to be activated because it is more active as it is than the palladium metal, so palladium 0. But the magnesium is slightly more active. The palladium will never be as active. If you put the ligand, it helps something else as well in terms of reactivity. What do you think the ligand does once you create a complex with the palladium? What might help when you create a reaction, when you do a reaction?
The electron density?
The electron density is connected more to the first reason.
Okay.
So it is true, but it's very connected to number 1. So if you these ligands, I don't know if you saw them. Some of them are really, really big, and this one has a phosphorus and 3 large benzene rings. So apart from the fact that they're this large, it might help you for one of the 2 or for both actually. So the fact that it's very large and very organic, what helps, you think? consider that it's not soluble completely in the solution, but
it's a good leaving group.
Yeah, the living group is also connected to the first one. So because it dissociates, so they can be a good living group. It actually helps basically the point number one that you say, because it increases the reactivity of the metal. But what really helps is also the solubility. So a big issue is it really helps, not too much the solubility because it's never completely soluble in the reaction, but it helps a better homogeneity of the reaction.
Yeah,
so
okay.
it keeps everything a little more in solution, so it swells a little more, and so the metal is more homogeneous. It's never completely homogeneous, but it's more. It makes the reagent more homogeneous. Connected to that, or actually something in between the first two, for instance, if you think about it, we said these ligands sometimes are really, really large. If you see in some of the examples that I gave you in the video, some of them are really, really, really large, and they can even dictate the stereochemistry. So a very good reason is using certain kind of ligands. It opens up the availability in the catalytic site. So basically, because of the hindrance of all these big ligands, everything makes the catalyst more, the central part of the catalyst more available. So larger ligands increase availability of the catalyst, of the palladium as a catalyst. Okay. So time is up for this breakout room. We'll keep it short today, otherwise I cannot keep the promise of leaving you by one. So we'll reconvene to the main room.
Okay.
Stand back. Oh no.
Oh, hello.
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 It's got all the steel in and stuff, so it's just literally just building it up.
Nice.
What is going on? We have more people now.
Yeah, I think we're finished.
Yeah, we went in the breakout room.
This is the only people left. Everyone else is gone.
I need to charge my headphones. What time is the next lecture? Does anyone know? 2, is it?
2.
I think 2, yeah.
Said my single short white. Who's that? Who's BO7? Oh, what?
Tartar still Ben.
Guys, let's just think something. This is not the typical question that I normally ask at the exam. This was very useful to understand this concept, because you may decide in the lab whether or not to use a good ligand, a certain ligand, or a palladium or a transition metal complex in your reaction altogether. Okay, so we discussed. I had the time to discuss only one of the breakout rooms, so some people know. Today, I would prefer to, because for the sake of time, I would prefer to solve the question just altogether instead of asking you. So there are, I named just 3 reasons. One is, for instance, the metal ligand complex are soluble in a various solvent and help a little bit the homogeneity of the reaction. So it's never a proper homogeneous catalyst because it's never completely soluble in any reaction. And if you remember from the green chemistry lab, it was never completely dissolved in the reaction. But actually, the fact that you can swell a little better or can dissolve a little better the catalyst into the reaction, so it creates a better dispersion, let's say, it really helps the mechanism and it makes the condition a little milder. Another reason is that, like we have seen from all the catalytic cycles, the adding ligands can dissociate from the metal, and like we have seen for the palladium tetrakis, it becomes palladium bis triphenylphosphine, creating a palladium 14 electron species. Okay, that helps in terms of reactivity because the palladium with full 18 electrons is not reactive enough. So by losing some of the ligands, or like we remember from the other exercise with the insertion of a carbonyl, for instance, without the dissociation of a ligand and the removal of a ligand to accommodate the carbon monoxide as another ligand, this will not help the reaction. So if you use just palladium 0, nothing of that will happen. And the last reason that I would like to focus on is that if you remember from the slides, from the videos actually, most of the ligands, sometimes I named some of them are quite exotic. And they're exotic not because people like just to throw some functional groups, is that they create large hindered substrate so that it can help the catalysis in different ways. Either they make the metal center more available for, let's say, oxidative addition, or sometimes it actually helps, and you'll see with Marcella, it helps the stereospecificity of the reaction. So controlling the shape and size of, and the nature, of course, of the ligand help different kind of catalysis, sometimes helping, for instance, making stereospecific reactions. Are we all okay with this? These are three of the various reasons why. So I just gathered 3 reasons of why do you always see different ligands, and why do you sometimes see in specific papers quite weird ligands. And you may think, why don't I just use palladium tetrakis? Because sometimes, depending on the reaction, you need to have certain ligands, and certain ligands dictate stereospecificity or reactivity of metals in different ways. We're all okay with that? Any questions on that? Anyone? Can you hear me, yeah?
Yes.
Because
Yeah,
I
we're fine.
No
We're fine.
I never know if I was muted or not. So I don't want to speak alone. Okay. Let's go back to another kind of exercise. Okay. So this one actually is, well, kind of similar to the other one, but it's different at the same time. So we will have stereochemistry. We're using different ligands. And we want to create this cross-coupling reaction. This is a particular metal. Do you remember at all what metal involves, what kind of, or which one of the cross-coupling involves tannate?
LICL, not tin. No, wait, where's tin?
The style coupling.
Yeah.
Okay. So this one,
Yeah.
normally, if you want to remember guys, I will never ask you to do this specific, I will never name a reaction and you have to solve the exercise because of the main reaction. That usually helps. If you remember, the boronic acid are for the Suzuki, the Negishi uses zinc, the Sille uses the tin. And sometimes it's quite important because we saw it in the video, changing just a little bit one of the reagents and using different metals, actually in the transmetallation step, revolutionizes the yield from 10% to 80, 90%. This is one of the cases. So what you need to ask yourself if you have this kind of reaction, a typical question, something like, you have all these mechanisms. Remember, I will give you everything on the slide. So if you follow all the mechanisms, you have the oxidative addition here. Then eventually you have all the different, here you use the tin. So the tin helps in the transmetallation step, so the coordination of the 2 reagents. But most importantly, you need to remember where and why, for instance, in this case, the tin palladium exchange. And this is, you want to remember that is involved, the tin is very much involved in the transmetallation step. What you want to ask yourself, and if you want to use it properly, is, in this case, why do you need to use a carbon monoxide atmosphere? In this case, in this specific case, we'll create a sigma complex. Remember that whenever you use palladium, whenever you use, sorry, I take this one again. Whenever you use carbon monoxide, it might also facilitate the carbon, the migratory insertion. What you need to know is, for instance, you want to ask yourself why the palladium catalyst has a benzyl group. In this case, it has a benzyl group. It's a different ligand. And usually the answer is hindrance. What you want to ask yourself, like we did for the boronic acid, is if you are using for retrosynthesis, yes, you're going to use a stannate here because it's a stiller coupling. How do you prepare a stannate? Because if I ask you for the retrosynthesis, you can say that you're going to use the thing with the stiller coupling. But how do I prepare it? So you need to also prepare some of the reagents. They don't come commercial, or not necessarily. So this one is a typical example. I would like just to show you. It's very difficult, I'm going to ask you something like that, but all this reasoning really helps your mind during the retrosynthesis. Because what you need to think about whenever you approach a retrosynthesis is, yeah, but then how do I do the synthesis? Because breaking the bonds, it's not breaking the bonds, and retrosynthesis is like going backwards. But making a disconnection for two particular carbon-carbon bonds, for instance, in this case, you should always ask yourself, can I really do that in synthesis? How do I do that in synthesis? How can I use proper reagents? And how can I show the synthesis? Remember that most likely the synthesis is a big part of the exam question. That means that it gives you a lot of marks. So in this case, remember, we don't need to do it here properly now, but this is a typical way how to create a stannate, okay? Any questions on this one? I'd just like to have an exercise in which I use everything, cross-coupling reaction, any kind of retrosynthesis, and especially all the questions that you should ask yourself once you approach retrosynthesis. We okay with here? We have 5 minutes to go.
Yeah.
So let's make use of the time in the best possible way. Remember, next time we are going to do, next lecture on Thursday, we're going to do the first two parts of the pericyclic reactions, which are also very important in synthesis. I do that in my lab I wouldn't say on a daily basis, but very often. So we'll try to be a little quicker. Today I had all the introductory parts, so I was definitely a little longer. Quickly, Sonogashira, again, and then I will leave you. Sonogashira, if you want to remember from the difference, Suzuki, boronic, still tin, Negishi, zinc, Sonogashira always is very typical because it always involves a triple bond. So again, if you have a retrosynthesis, you have a triple bond, and you don't know how to disconnect, you might immediately think about, maybe I can split into molecules using then the Sonogashira coupling to recombine them, okay? Oxidative addition is always the same. The most important part of the Sonogashira coupling is that it uses copper 1. It's always a copper 1 attached to the alkyne, because otherwise this transmetallation step does not happen. Okay, that's a very important part of the Sonogashira. It gets into the other extra cycle, but in my case, it's not as important. So I will leave you on the slides to watch some other particular ligands used for Suzuki coupling in this case. You can see that there are so many which are very, very different, very peculiar. Believe me, I will not ask you any of those for the exams. I would like just for you to appreciate that a lot of chemistry can be done on the ligand instead of just on the cross-coupling reaction itself. Okay, the last few slides are from last year, which were supposed to introduce you to the green chemistry lab, but you actually did the green chemistry lab already, so there's no need we use them. So I will stop sharing now, and in the last 2 minutes, I will ask you, how did it go? What do you think? Clearly, we need to get it faster, especially in the breakout rooms, but I think everything will be faster once we start playing with it. Any comments, questions, suggestions on today's lecture? Are you happy to do the same kind of format next week next Thursday?
Yeah.
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 You're following?
Yeah.
You're happy? If I'm too quick, if I'm too slow, please tell me. I will try to readjust. Believe me, this Zoom lectures is very new for me as it is for you. So as I said, everything can be fixed. Most important for me is that you understand this part, because then you're going to use it. Okay? If there are any other questions, please email me. Otherwise, I'll see you on, I'll see you, 21 of you tomorrow in the lab, and all the rest all together in the 5-ish on the next class on Thursday. Okay?
So cool.
Bye, guys. See you tomorrow.
Bye.
Bye.
Thanks, Lena.
Bye.